Okay, good afternoon. Very simple announcement. We have assignment 7 waiting for you. Deadline is next Monday. And then the assignment 8 is a longer one. So I haven't decided the deadline yet, but I think I can push it a little bit towards the reading week, because we will have two more weeks of lecture, then we have 1 more week of break. But this reading week is supposed to be for you to read. So I think I will maybe set one assignment 8, to be at the beginning, the deadline of which to be at the beginning of the reading week. And then assignment 9 will have the deadline towards the end of the reading week. Okay, and that would be a very good pace. And after the reading week, we have some very strange arrangement. We will have 3 more lectures. Then that is the end of the course, because we have a Easter break in between. So assignment 10 should cover the final 3 lectures. Okay, so that's the plan. So after today, we have 7 lectures left, if I remember correctly. Okay, and because of the midterm, we are running a little bit behind, so there's no exercise classes tomorrow. We will continue to our exercise classes from next Thursday. Okay, so that's all for the announcement, and thank you for coming to the midterm. So far, I didn't receive much complaint about this midterm. So my mic is unclear. Is it true for everybody or just for? Okay, I don't want to keep talking with this problem. So please, what about others? So I received a complaint saying that my voice is not clear. Hello, hello. So the student who complain about this, you might need to check your device, because other people seem to say it's okay. Loud and clear, really? Loud. Okay, clear. Loud. I will soften it, okay? Okay, so I hope you can fix this problem. Okay, coming back to the midterm, I think it's a rather standard one. It's not too unfriendly. And in particular, the last question about black body radiation, there's one piece of physics which I hope you got it. That is, I asked you to calculate the chemical potential. Okay, so that calculation will be important for our statistical mechanics later. Okay, and if you have done it correctly, you get mu to be 0, precisely 0. And that is why we don't need the fundamental equation for the open system. That is why at the beginning, I asked you to assume this is a closed system. Then I asked you to take it as an open system. And then, well, the reason that both of them can work is simply because the mu term is 0. Mu is 0, so mu times dn will be 0. That is why you can use both equations. And this is a very special case for photons. And the reason we can do this is because you can create particles. You can create this kind of massless particles. And we are going to look at this situation when mu equals 0, again, when we do statistical mechanics. Okay, the other thing is I get a little bit of somebody say that they are not comfortable with the Lagrange multiplier. This is not something I can spend a lot of time to talk about, because this should be in other courses. I can only use it here. So I will offer something quick. I'm not going to derive all this again. But I can kind of guess based on my experience with the previous classes. that you are probably not comfortable because of the fact that you have a lot of you have an infinite number of variables here. Okay, what do I mean? I mean this n, j, right? Remember, my j takes is a label, so my j takes values from 0 or 1 to infinity. So you have many of them, and therefore you have all these d n sub j, again many of them, and therefore you probably are not comfortable. This is my guess. I'm not sure what is the uneasiness. Okay, so now one thing I can tell you is you can try to work on a simple problem and use Lagrange multiplier. You know the answer very well, and that is a test case for you to try. So I'm going to offer you one problem, and this is a standard problem. Okay, let me describe it this way. Suppose you are you go to a new country, and you are entitled a piece of land. Right? You are given a piece of land, but you are told that the land has to be rectangular in shape and the area cannot be more than 100 square meter. Okay, so let me translate this question for you. You are given a piece of land. You are asked you cannot be too greedy, and this area has to be rectangular in size, and the area cannot be more than 100 square meter. Okay, and then it's a standard question that you deal with before. The question is, what is the optimized length of material that you can use? Okay, and what is the shape? Now I think you know the answer already. Okay, let me put it in the mathematical form. Okay, so I'm going to call this x and y, then this is your area, right? This area is xy, x times y. I make it very simple so we can get this done quickly. You can cook up more complicated problem. And here you are asked to solve a particular problem, right? You are told that this is not more than 100 square meter. Of course, you set it to exactly 100. You won't be so stupid, right? And this is the thing in thermodynamics we call it n. This is our constraint. This is basically telling you my area. In thermodynamics we use this number. We use this n that you might not remember is a constraint. It's a constant. Okay, so if I don't worry about this 100, I will just write this as x fixed. This is x fixed. This is fixed. Okay. And therefore, when you do ds, you get 0. Okay, so this is your constraint. This is a constraint. And what is ds? ds in this case will be x dy plus y dx. Okay. And now you talk about the material you need to buy to build this. So that is the fence, right? So this is you want to partition it. You want to find your own area that you don't want other to come in, so you build the fence, and this fence is 2x plus y. Okay, and now this is also 0. You want dl to be 0, but the meaning is different. This ds is 0. It's because you take the differential of a constant, so this is 0. But dl equals 0, this is really evaluating a stationary point. Okay, so what I can only say is that they are both 0, but the meaning is different. So this is because I want a stationary point. I want to find an extremo. I cannot tell whether this is minimum or maximum because I stop at the first differential. Okay, but in thermodynamics, sometimes the problem is clear. In thermodynamics, we know we want to maximize things. Okay, and now what do? You get 2x plus 2dx plus 2 dy. Okay, so this is because you want to optimize. This is like our log. We take the d log omega. So this is optimization. And up here, this is constraint. So they both take 0, but so this is constraint. All right, so now you are done. You have everything you need. You just write down the constraint equation. So I want to satisfy dl equals 0 and ds equals 0 simultaneously. So this is my Lagrange multiplier. Multiplier goes with the constraint, and this is the standard setup. Okay, and then you plug it in. You can have 2 dx plus 2 dy plus lambda times x dy plus y dx, and this has to be 0. Okay, and then you continue this, you will find x equals 0, x equals y. As expected, you know this has to be a square. Okay, try it. Just 2 more lines, you get this. And also from here, this dy, I could have call it dn1, this is dn2, and these are all these dn's that you are probably not comfortable with. Okay, and also from here, this constraint equation tells you dx and dy are not independent, but we can arrange it such that we will get everything in front of this d whatever to be independent. This argument has been presented to you last time. Okay, so this is really a simple question for you, but hopefully you will get it. Once you get it, you feel more comfortable. So I get 2 emails about this. Now this is so simple. You don't really need Lagrange multiplier. So when do you need it? Now you need it for thermodynamics, right? For our course, this is our starting point. We can get very far. Today we are going to really show you what we can get. Now, typically, this kind of problem is set up like this. For example, suppose you have you have a mountain somewhere. Let's say Mount Shan. I'm looking at Mount Shan. Can I? Is there Mount Shan? No, there is not. I'm looking at some mountain. I can come up with the now if I draw the height. All the points on this line is the same height, so I can have my peak of the mountain like this. So this is geodesic, right? So the peak of the mountain is somewhere here. So this is increasing height going this way from out to in. And suppose let's say for simplicity, I arrange my origin to be at the peak. So I will have a function like this. So I can set up my coordinate system like this. Origin at the peak, and therefore this height profile h is a function of x, y, and you know you can optimize this. Okay, now when do you need Lagrange multiplier? You need Lagrange multiplier when you have a constraint. And what is a likely constraint here? For example, a constraint will be like this. You have this mountain, and you are asked to build a cable car to go to the mountain, but unfortunately you are not very good, so you deviate a little bit. This is your path of the cable car, and now this is your constraint. So the question then is, you are asked to optimize, find the maximum or the minimum. Now here is clear that is a maximum. Find the maximum height subject to the constraint. If you know the equation for this cable car, this track, you know the maximum will probably be somewhere here, not at the origin, once you optimize it properly. Okay, and this is when Lagrange multiplier is powerful. To solve this kind of easy problem, you don't need Lagrange multiplier, but hopefully this is enough for you to appreciate that what we are doing here is not that crazy. It's maybe the notation is a little bit messy for you, but once you really understand the meaning of all this notation, it shouldn't be that problematic. Okay. All right, and if you want to learn more, you can always find some textbooks. There are lots of materials out there that you can self-learn. Okay. All right. So I want to pick up from what we did last time and really do thermodynamics. Okay, before the midterm, what did we do? Before the midterm, we really only did statistics, right? If you think carefully, if you go back and look at those materials, I do not recall any thermodynamics. We really just play with probability theory. But this is a course about thermophysics. So today we need to really connect these two. Okay, so this is for the purpose of today's lecture, I will write down what are the important points. Before the midterm, we talk about distinguishable particle or localized particles, localized in the sense that we know the address and we know how to describe them. How do we describe them? We describe their energy levels, the possible energy level. We label them like this: epsilon 1, epsilon 2. It's a long list, and epsilon j, and so on. And when we did counting, we look around and we ask how many particles are in epsilon 1, how many particles are in epsilon 2, and so on. And this point is important. I want you to keep this in mind right now. When we did the counting, when we did this log, we really only care about this n, this number of n's. Now you might find this is a little bit strange, right? We didn't talk about anything about the particular energy values. We only look at these n's and we don't really attach the energy value, although we know there's an association between them. Okay, and this point will come back today. All right, so keep this in mind, the equation of calculating omega. So that is this thing here, this omega. I might as well write it down. This omega you calculate based on this formula, the total number of particles, and then divided by how many particles are in the epsilon 1, how many particles are in epsilon 2. So this is really just a description about the number, the occupation number. There's no knowledge about the energy values at this point. Okay, so this is what we did. And I already mentioned you should see this as the equilibrium occupation numbers. That's to say, once you optimize this omega, you will reach the thermal equilibrium. And at the equilibrium state, what are the distribution of the particles? Okay, that is the interpretation. And that interpretation is related to this line here, right? So if you have a small number of systems, it's not meaningful to discuss this. Look at the coin problem. Actually, look at the system with 3 particles. I managed to list everything out, but I did not see any sharp distribution. And look at the case with 6 particles. You also did it, and you know the situation becomes a little bit more realistic. And now for the thermodynamic system where we have a huge number of particles, you will find that all this sum can actually be dominated by one particular state, and that is one particular little omega, and that's the omega with the maximum number of microstates. Okay, and that's why we drop this summation sign. This is the case when we have large n. Okay, that is to say you will have something like this. Now, the total number of omega, of course, depends on this, right? You sum up all this, right? Right. So this is omega, little omega 1, little omega 2, little omega max, little omega 4. But when you have a large number of particles, you will find this is sharply peak. And therefore, the summation is dominated by one particular value of k. And that is why we can write it down like this. So this is only true when you have a very large n. Okay, so that is also another thing to keep in mind for for today's lecture. And therefore, from here, what do we get from here? We can manipulate that. We did that already. We take the log. We want to maximize omega, but equivalently, we can maximize log because that is more convenient, and also because we know how to approximate this. And the approximation for large N is Stirling approximation. Okay, if I take log, we know we will get this. Log of nj factorial. All right, and you do your differential d of log omega, and there are a few lines here, and eventually you get this. This. All right, so this result is something we derive. Actually, I spent quite a bit of time to derive, and I'm going to use it again. So now this is a recommendation for you. If you have a piece of paper, small piece of paper in front of you, please write this down and stick in front of your screen. Make sure you don't cover my writing, and we are going to need it at least twice today. And so when it shows up, you will recognize it. Okay, so this is the equation in the box is what we are going to is what we will need later. Okay, so that will really help you to follow. Okay, so we did this, and the next step is the Lagrange multiplier step. So we will have two constraints, the constraint being dn has to be 0. So we have alpha dn, and the total internal energy has to be 0. So we have this. Okay, so alpha always goes with number and beta always goes with energy. This is somehow universal, at least for the textbooks I have inspected, except the sign. The sign is not universal. Some people put minus, some people put minus plus. You can get all kind of combinations, so you need to be careful. Okay, and from here you get from this last line, you do it properly and go through this argument about Lagrange multiplier, you get your n. And this is the equilibrium distribution, right? Because you have many j's here. Okay, so you get all these nj's, they can be written like this. Exponential minus beta. All right. And I also told you, when you did the 6-particle case, I already asked you to guess what is the form. And the form will be something like this. It's an exponential factor, a Boltzmann distribution or Boltzmann-like distribution. We need to interpret beta before we can confirm that we have a Boltzmann factor. Okay, and finally, we define the statistical entropy, which is related to this same, exactly this omega, big omega. Okay, you take the log, you maximize it, and back then I explained to you the beautiful connection between them. Now, to be honest, at this point, we began to do thermophysics. And before, we really simply just do the counting, really just doing probability theory. Okay, and this is what I call postulate 3. Postulate 3. Okay, so I explained to you why this is a good definition. We define the entropy, the absolute value of entropy, to be log of proportional to log of omega, and Kb is a Boltzmann constant. All right, so write this down: d log omega. This whole thing in the red color box. Okay, now we want to try to understand this. What is this beta here? The meaning of this beta. The meaning of alpha is kind of easy. We already know the form. So let me write this down again. We have this nj like this, written like this. Okay, and what else do we know? We know if we sum over nj, you go to your system, you go to all the energy levels, you read the values, right? How many particles are there in this level, right? And you sum them up. This is something you must not forget. This will give you the total number of particles, which for us is a constant. Okay. All right, let's do the sum. You will have sum over j exponential minus j minus alpha. Okay, and we usually call this a. It's not necessary to keep writing this a. Okay, so a is e to the minus alpha. Okay, and this has to be n, right? So so from here to here, I'm really doing the sum. Okay, so how do you look at this? This is really a normalization factor. This is a. In such a way that you want this equation to be true. Okay, so you adjust your a such that you can achieve this goal. So this is really, it takes the meaning of normalization, just like what you learn in other courses. You adjust this a. This is independent of j, right? So you just make sure you are able to reach to satisfy this equation. Okay, and sometimes we like to evaluate the ratio. So this is trivial. So we also write it like this, right? A, there's no index j attached, so you can take it out of the summation sign, and this is it. Okay. All right, so this is simple. This is alpha. Now beta is more interesting. So I'm going to borrow a system like this. So this is what we had last time. Now here, this system. Okay, so we talked about entropy last time. I will let you look at this. This is a slide from last time. We talk about why we can define it using log, but anyway, the purpose is to really recreate this and go through the same analysis, but now using thermodynamics. Okay, so let's do exactly this. Yeah. Okay, let me define things carefully for you. I'm going to take my system. This is isolated. You cannot see from the outside world. So this is my universe. And what I want to do is I will imagine having a rigid partition. I'm going to partition this into two subsystems. Okay, this is a rigid system. Then I'm going to do thermodynamics based on this kind of setup and apply things logically to see the meaning of beta. Okay, so I'm going to call this system 1. So according to my notes, yes, I call the one on the left system 1. So I have N1 particle, and on the left I have N2 particles. Okay, and further, I do not, this is a rigid wall. I do not allow particle exchange either. Okay, so I can only allow the exchange. Okay, the exchange of heat is fine. Okay, this is allowed. And the exchange of particle, not allowed. Okay, so I'm going to just analyze this simple system, and the notation is going to be messy, so please follow me. carefully. So I'm going to attach everything to 2 with a dash, a prime. Okay, so this is the primed system. And the note is better. The note I color code system 1 and system 2 for you. So it's more readable. But here I will try my best to say things out. So if you follow me, you will also get it. Okay. What do? We write down the constraint, right? Based on this system, we can write down the constraint. So everything to do with system 1 will take this kind of symbol without the dash, without this dash, okay? So this is system 1. So if I sum over all the energy levels for my subsystem on the left, system 1, this better sum to N1. This is a total number of particles for system 1. Okay, so for system 2, this is easy. I will have to label it differently. I will have n sub j dash, and if I do it similarly, I will get n2. All right, and this is the number constraint, and the energy constraint. In the non-interacting case, I will have epsilon j nj. Sum over OJ, and that has to be the total internal energy U1. And for the system, for system 2, I will have epsilon J and J, and this will be U2. Okay. And this N, N's, the capital N, N1, N2, U1, U2 are constant. Okay, so then I get my constraint equation right away. So I have dN1 is 0, dN2 is 0, du1 is 0, and du2 is 0. Okay, something is wrong with this line. So if you follow me, you should be able to tell me what is wrong. The last line here, I intentionally make a mistake for you to try to pick up. Anyone? You can type. Type a direct message to me. Let me repeat this. I set up the thermodynamics problem for you, and I write down the constraints, but the constraint is not quite right. You need to modify it for me. Okay, excellent. Actually, nice. I think it's good. This maybe shows that you really follow this well. Okay, so what I can at most say is this is 0. Okay, because of the setup, I allow the exchange of heat, even though I do not allow work done because this is a rigid partition. But because I can exchange heat, I can exchange the internal energy. So du total has to be 0. Okay, so from here I can write. I will write it down right away because I need it soon. So I will have du. What is the du in the non-interacting case? I will have this one, du1 plus sum over j epsilon j dash dnj dash. This is exactly this one, so it has to also be 0. It has to be 0 too. Okay, be careful. I have already done the differential here. Okay, so here you get du1 plus du2 is 0. So du1 is you have to take the differential, and we don't change the energy level because we keep the volume constant, right? So therefore, this process, the only thing that can change is n. So we have to write it down this way. Okay. Partition function, not yet. Okay, so next, still using the two subsystem. Crazy. Okay, sorry. All right. What is the next thing we can do? The next thing we can do goes back to last lecture. What is the total omega for the joint system? Right now I have N1, N2, so I can have the omega for the left-hand side. I can also have the omega for the right-hand side. And what is the relationship between these three quantities? Do I use a plus or do I use a multiplication? Or this? Which one? Any idea? Okay, this is less successful. Okay, I see now this is the correct one. The reason is explained in the past. This is really to do with probability theory rather than thermodynamics. Okay, and that is also the reason why we want to use a log, because we want to be able to count this probability correctly. Now, go back to my last lecture. For the student who say plus, go back to my last lecture, or go back to a little bit a while ago when I talk about dice. Okay, there I already mentioned something about this kind of operation. So this you have to multiply them. Okay, so let's do it. So I will have to, for the system one, I will have this, right? So what is omega 1? Omega 1 will be this. Okay, I will have n1 factorial divided by little n1 factorial times little n2 factorial times whatever. So this is written in a compact way. And therefore for system 2, I will have something similar. I have n2, and then I have this result, nj prime factorial. Okay. Now this is the messy part. I don't quite like to do it, but I would try to be careful because it's easy to make mistake. So I don't want to do both. I will just do one. I don't want to do 1 and 2. I will just do the one with unprime. Okay, so I have to take log. So I have this minus this product. Once I take log, it becomes sum of nj, like this. Okay, so this is 1. Okay, once I take log, this also becomes a plus here. And I will have everything identical, except I need to change n1 to n2, and then little nj to little nj prime. Okay, so you can do yourself or look at my note. My note is color coded. It's very nice, I think. All right, so now I want to do something a little bit different, but the end result is the same. I want to show you two ways of doing things. Last time, when we only have this, I told you n is a constant. I'm going to, the big N is a constant. I'm going to do the differential. This is going to be 0 anyway. So I can do it that way, or I can do it the other way, which I'm going to show you now. I'm going to do the Stirling. Okay, so this is n1 log n1 minus n1, and then I'm going to do the Stirling for this thing inside. So the reason I want to do it this way is I want you to recognize something which is useful for you to manipulate this. Today, we have a lot of manipulation like this. It's rather tedious. Okay, so this is done for the system 1. Okay, for the system 1. And for the system 2, you have something similar. Okay, so I use a sterling. So okay. All right, so let me write this out. Actually, I really just want you to recognize that point. So I have 4 terms here. So this is minus and plus. Right? You can see 4 terms. Okay, and then there are another identical one. So this is 1, 2, 3. Right, 4 terms that I can sum together. Okay, 2 of them are identical. Again, use your chat and tell me which ones are identical. Anybody else? I get only one answer this time. And this is the point of doing things like this. I want everybody to recognize this, at least at this simple level. Okay, excellent. Okay, quite good, quite good. Okay, so the sum of this nj, remember the sum to n1, so actually this cancel this. Okay, that is the reason why I want to do it this way, because sometimes you get later you will see today at the end of today's lecture, we will get to the point that you have a lot of things like this. You need to recognize what how to do cancellation. Okay. All right. So now I'm ready to do the log. So once I do the log, capital N is a constant, so this one will be gone. The term 2 is gone. Term 4 is gone. So the only thing I need to do the differential is the term 3. Okay, so I will write it step by step. I only have 3 left. Okay. Sorry, missing one N. Okay, plus the equivalent term here. Okay, so what do we have here? When we do it, when you expand this and really do the differential, you get exactly that equation. I want you to box. I want you to write and stick in front of your screen. Okay, so you have sum over log j, log nj, dnj. So you can kind of think a bit differently and you still get to the same answer. Last time, remember, we didn't do it like this. Okay, so I might as well put in the prime system. So I will have sum over j, log of nj dash dnj dash. Okay, right, remember what I asked you to keep in front, and where's it? This one, d log, is written like this. Now we have 2 systems, so you get d log is this plus the other one, and this has to be set to 0. Okay, so how many constraints do we have? We have 3 constraints, right? We don't have 4. I told you setting 4 constraints is wrong. Okay, so let's do 3 constraints, and this is what we want to optimize. So we have, let me check my note for a bit. I need to make sure the sign is consistent. So we will have this that we need to set to 0. So we need to set this to 0. And then we need to set dn1 to 0. So I'm going to give a multiplier alpha 1. And then we have to set dn2 to 0. So this is multiplier alpha 2. Then next thing is the sum of u1 and u2. We need to set this to 0 too. So we are going to give the multiplier beta. Okay. So I will have minus d log of omega plus alpha 1 dn1 plus alpha 2 dn2 plus beta. Okay. Okay, next we copy from here. I take a minus d log, so this minus sign is gone. I will have sum over j